All right. Today, we're tackling one of the most fundamental and, let's be honest, kind of frustrating rules in all of computer science. It's a really powerful idea called Rice's theorem.
So let me just start with a question that, on the surface, feels like we should have solved it by now, right? We've got AI that can create unbelievable art, we've got cars that are driving themselves. So why on earth can't we just build one single tool that automatically finds all the bugs in any program? It feels solvable. But the truth is, it's not just hard, it is mathematically, provably impossible.
And to understand why it's impossible, we first have to imagine the dream, the quest for what you could call the ultimate bug checker.
I mean, can you imagine this? Every single software developer on the planet wishes they had this tool, a single kind of magical program where you feed it any other program, tell it what that program is supposed to do, and it just gives you a perfect, simple yes or no answer. Yep, code's good. Or nope, you've got a bug. This would literally save billions of dollars, countless hours, and prevent who knows how many headaches. It is the absolute holy grail.
Okay, so why is this holy grail totally out of reach? Well, the reason comes down to a really crucial distinction. It's not about the code you can see, it's about what that code actually does.
Let's break this down. On one side, you have syntax. Think of this like the grammar and spelling of your code, the text you type, the variable names, where you put the semicolons. It's just about how the program is written down. But on the other side, you have semantics. This is the deep stuff. This is the meaning. What does the program actually do when you hit run? What's its behavior, its output? That's semantics.
And this right here is the absolute key. Rice's theorem doesn't care about the syntax. We actually have lots of tools that can check for syntax errors pretty easily. No, this theorem is aimed squarely at the behavior, the semantics. And that, my friends, is a much, much harder target to hit.
So, with that difference in mind, the code versus what it does, we are now ready to look at the unbreakable rule that solves our mystery once and for all.
Now, the theorem uses a fancy-sounding phrase, a non-trivial semantic property. I know, it sounds super academic, but it's actually pretty simple. Semantic just means it's about the program's behavior, and non-trivial just means it's an interesting question. You know, a property that some programs have and others don't. For example, does this program ever crash? Well, some do, some don't. That makes it a non-trivial property.
And this brings us right to the heart of it. Rice's theorem states, with all the power of a mathematical proof, that all of these interesting questions about a program's behavior are undecidable. Now, undecidable is a huge word in computer science. It doesn't just mean we haven't found the answer yet. It means an answer cannot be found by an algorithm. It's not that we're not smart enough to build the tool, it's that such a tool cannot possibly exist.
And this isn't some new idea either. This mind-bending limit on what we can compute was proven way back in 1951 by Henry Gordon Rice for his PhD. Talk about a bombshell of a dissertation. It's been a cornerstone in the field ever since.
So how can we be so sure this is true? Well, the proof is this beautiful, elegant little trap. It's a classic proof by contradiction. Let's walk through it. First, just pretend with me. Let's assume the impossible is possible, and you do have a magic tool. Let's say it's a tool that can perfectly identify if any program is a squaring function, a program that just takes a number and squares it. Okay, now for step 2, we get sneaky. We build our own little program, let's call it Tricky T. And here's what Tricky T does. It takes some other program, any random program in the world, we'll call it program A, and it tries to run it. And now for the kicker, the key part in step 4. Only if program A eventually finishes running and halts. Only then does our Tricky T program start behaving like a squaring function. If program A runs forever, Tricky T just sits there and does nothing.
You see the trap we just laid? Our Tricky T program only acts like a squaring function if and only if program A eventually stops. The two behaviors are now completely, inextricably linked. So think about what this means. If we point our magic squaring function checker at our Tricky 2 program, what happens? If the tool says yes, this is a squaring function, we now know something deeper. We know that program A must have halted. And if the tool says no, we know program A must be stuck in an infinite loop. All of a sudden, our little magic tool has been weaponized to solve the famous halting problem. And there's the checkmate. Because the legendary Alan Turing already proved that the halting problem is unsolvable. It's the original impossible problem of computer science. So if our magic tool's existence would let us solve an unsolvable problem, well, that's a paradox. It's a contradiction. And the only way to resolve it is to admit our initial assumption was wrong. The magic tool can't exist.
And the genius here is that you could swap out "is it a squaring function" for almost any interesting behavior. Is it impossible to build a general tool to know if a program halts on input 0? Yes. If it halts on every input? Yes.
If it ever returns the number 0, yes. If it's secretly a virus, yes. And for our original question, is it completely bug-free? Yes. For the general case, it's all impossible. The implications here are just huge.
Okay, so that sounds pretty depressing, right? If the perfect tool is impossible, do we just give up and go home? Of course not. This is where engineers get really clever. So let's look at the workarounds.
So we can't solve the whole problem, but we can chip away at it with specific, constrained solutions. For instance, some programming languages cleverly sidestep the theorem by checking the syntax, not the behavior. They catch certain kinds of silly errors before the program even runs, like if you try to add a word to a number. Other tools use something called abstract interpretation, which is kind of like an educated guess. It can't promise to find every single bug, but it's really good at spotting common patterns of mistakes. And for the really critical stuff, like software for airplanes or power plants, engineers use even heavier duty techniques like model checking, or even require programmers to write out mathematical proofs that their code is correct. It's not one magic bullet, but a whole toolkit of smart approaches.
So let's just pull all this together. What is the big, final takeaway from this deep dive into a fundamental limit of computation?
It's really easy to hear about Rice's theorem and think it's a story of failure, a story about what computers can't do. But that's really not the right way to see it. It's an incredible discovery. It's like someone handed us a map of the computational universe and showed us where the edges are. It draws a clear, definite line in the sand between what is computable and what will forever be out of reach.
And that leaves us with a final and pretty deep thought. We live in a world that is completely run by unbelievably complex software. Our money, our communication, our transportation, everything. So if we know for a fact that it is mathematically impossible to build a tool that can prove that software is perfect, what does that say about the enormous trust we place in those systems every single day? Definitely something to think about.